Alright, so here we are with part 2 of section 5.4, and we're taking a look at applications of definite integrals. Specifically, we're taking a look at this one right here. We're saying that we want to take a look at this application of a definite integral. Now, upon first inspection, when you first look at it, you say, oh, that's just the fundamental theorem of calculus part 2, but the fundamental theorem of calculus part 2 says the integral of a to b of little f of x dx is going to be equal to f of b minus f of a. And these two things are different because little f is different from big F prime, and that's what we're going to take a look at. Right? We're taking a look at an application of definite integrals, which is why this is f prime rather than just little f of x. So what we're saying here is that if we know that our function f prime represents a rate of change of some function f of x, then the integral is going to give us the change from a to b for that function f. All right, now I know that's a lot to handle, but let's just break it down and see what it means. All right? Suppose that f prime was a rate of change. Now I'm going to go with the one that you know the best. Let's say that f prime was velocity, and we were going to do the integral from 1 to 2 of velocity dx. Well, the antiderivative of velocity is going to be position. So it's going to be position at time 2, or what letter do we use for that? We use s, don't we? Position at time 2 minus position at time 1, and position at time 2 minus position at time 1 is going to give us the change in position, the net change from time 1 to time 2. And so what this application section is about, it's about all the different ways that a rate of change can show up in an integral, and what will it mean. Now, in this textbook, they call it the net change theorem. I've seen other books call it the total change theorem. A bunch of different names because there's a bunch of different authors. But basically, every single one of them says the same thing. They say that if you take the integral of a rate of change, you're going to get the position at time b minus position at time a, or the volume at time b minus the volume at time a, or the cost at time b minus the cost at time a. So there's lots of different ways that this thing can be applied. For example, if v of t is the volume of water in a reservoir at time t, I'm just going to stop right there. I just want to highlight this because we really need to understand what we're talking about here. Right? If v of t is the volume, then something like v of 3, what would v of 3 mean? Well, that would be the volume at time 3. Or what would v of 7 mean? It would mean the volume at time 7. Right? Then v prime then. Well, what does v prime mean? If v tells you volume, then v prime tells you how your volume is changing. So let's say that there's a reservoir and there's water flowing into the reservoir, then v prime would tell you how much water is flowing into the reservoir as a function of time. So then what would this integral mean? Right? Well, if we do the integral of the water flowing into the reservoir, the v prime of t here, we're going to get a volume at time 2 minus a volume at time 1, and volume at time 2 minus volume at time 1 is going to give us how much water went into the reservoir from time 1 to time 2. So if time 1 down here represents 7 a.m. and time 2 over here represents 3 p.m., then this equation right here is going to tell me how much the water level changed, how much water went into the reservoir between 3 p.m. and between 7 a.m. and 3 p.m. And so we find how much something changes by taking the integral of the rate of change. I want to say that again. We find how much something changes by taking the integral of the rate of change. That's what it's always going to be. Okay? Chemistry. If you can measure a rate of change of a reaction, then the integral of the rate of change of a reaction is going to give us the total change. So if C of t is the concentration of some sort of a product, and you can measure how fast that concentration is changing, then C of t2 minus C of t1 is going to be the net change, or the total change, increase or decrease, of whatever that concentration product C is. right? Population growth. I'll skip over the mass of the ride. It's not an easy one to talk about. If we knew the rate of growth of a population, if we know how fast babies are being born, if you take the integral of how fast babies are being born, the rate of change of the population, you get a change in population. Right? Integrate the rate of change of growth. Right? There's a weird one that shows up in economics. Economics is its own beast, so they do think silly. They use this word marginal all the time. Marginal always means derivative. I don't know why. That's just how economics works. So if you see marginal cost, that means the derivative of the cost function. If you see marginal profit, that means the derivative of the profit function. If you see marginal revenue, they're talking about the derivative of the revenue function. Right? So if C of X is the cost of producing X units of a commodity, right? So let's say we're making something. We're going to make candy bars. Right? So then C of X is going to tell me how much it costs to make X units of candy bars. So C of 1,000 will be the cost for 1,000 candy bars. Right? So then what does C prime tell me? Well, C prime is the rate of change of the cost of candy bars. So how much does it cost to go from the 100th to the 101st candy bar? Right? Because as I scale things up, costs aren't going to stay linear. So this function measures how much that cost changes by. And so what's going to happen when we integrate the rate of change of the cost? It's going to give us the change in cost. So if X sub 1 was the 100th candy bar and X sub 2 was the 101st candy bar, and C of 101 minus C of 100 is going to give us the rate of change, or the total change between the 100th and the 101st candy bar, or essentially the cost of producing that 101st candy bar. Right? If an object moves along a straight line with position function s of t, then its velocity is the derivative, which is v of t. So if you integrate velocity, what do you get? You get position at time 2 minus position at time 1. The position at the end minus the position at the beginning is going to give you your displacement. Okay? And so if I want to know the displacement of an object, I take the integral over that time interval of the velocity. Right? Now, think back to when we talked about objects before. Do you remember the difference between these two words? Distance versus displacement. End position minus start position is displacement. Distance traveled, we have to find the left, the right, and add them up, right? So if displacement is found by doing the integral of v of t, distance will be found by doing the integral of the absolute value of v of t. Because what the absolute value does is the absolute value takes everything that's left to right, makes it all movement to the right, and then you can find the total distance traveled because it'll turn it all into right movement. I know what you're thinking. What does that mean? Well, here's a lovely picture to explain it. Here I have a velocity function over here on the left. Right? I have a1, a2, and a3 in a velocity function. a1 and a3 here and here, these are going to represent movement to the right because it's positive area under the curve. Positive area here represents distance or movement to the right. Right? The middle piece here is going to represent movement to the left. And so if I add up 2 rights and subtract off 1 left, that's going to give me my displacement. Okay? So my displacement would be the area 1 minus the area 2 plus the area 3. My distance traveled would be, well, what's the distance to the right? We moved in area 1. What's the distance to the left? We moved in area 2. And what's the distance to the right? They moved in area 3. Right? If you think back, we've done this already. We didn't use integration for it, but we've done this already. Remember when we made those pictures that look like this? And we said, okay, if this is time 0, and if this is time 3, and this is time 5, and over here is time 7, if we wanted to find the distance on the interval 0 to 7, we would just simply say, well, here's where you started, here's where you stopped. I'm sorry, I said distance, didn't I? I meant to say displacement. Okay, you say here's where you started, here's where you stopped. How far apart are those? If we wanted to find the distance traveled, we'd have to find this piece, and then this piece, and add them all together. Okay? The way that we do that, this piece, that piece, this piece, the distance traveled with calculus, is we take the integral of the absolute value. Okay? All right, now something that you should be thinking about. You should be thinking that, hey, wait a second. I never once saw in the table up there anything to do with taking the integral of an absolute value. In fact, if I go back up to it, there it is. Do you see an absolute value anywhere? I know, there's an absolute value here. I don't care. I'm asking you, do you see an absolute value in any of the integrals? I don't see an absolute value in any of the integrals. And if there's no absolute value in integral, that means that I cannot perform an integration on something where there's an absolute value in the integral. So now what am I saying? I'm saying that down here, what this formula right here tells you to do is actually something you can't do. You can, whoa, wrong marker. You cannot do the integral from t1 to t2 with the absolute value of v of t dt. It's impossible. There is no such thing as an absolute value antiderivative. So what we have to do is we have to make use of a property that I'm sure you remember. The property said the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral, and I'm going to get rid of this so I have some more space, the integral from c to b, sorry about that, kind of messy, of f of x dx. So what we're going to do is we're going to rip the integral apart. We're going to rip the integral apart so that we can make some of them be the positive pieces, some of them be the negative pieces, and then we're going to be able to get rid of the absolute value by doing that. All right, so let's take a look at an example here. A particle moves along the line so that its velocity at time t is given by the function v of t equals that mass measured in meters per second. Find the displacement of the particle during the time period 1 to 4. All right, my job is to find displacement, so I know what that means to do. Okay? If I wasn't in chapter 5, I would say do this. Do s of 4 minus s of 1. But I don't have a position function, so I can't do that. So because I am in chapter 5, though, I'm going to make a use of something that I know how to do. That is, I am going to rewrite displacement as an integral. And I'm going to say the displacement is going to be equal to the integral from the start time to the stop time of the velocity function v of t dt, or more specifically, the integral from 1 to 4 of t squared minus t minus 6 dt. Okay? So I am asked to perform a definite integral, and because it is a definite integral, I know I'm going to have a numerical value as my final answer. So my displacement is going to be first term, t cubed over 3, minus second term, t squared over 2, minus third term, 6t, all of this evaluated from 1 to 4. Okay? So that's going to be 4 cubed over 3, minus 4 squared over 2, minus 6 times 4, minus 1 cubed over 3, minus 1 squared over 2, minus 6 times 1. 4 cubed is what, 64? So I have 64 thirds. 4 squared, 16, 8, minus 24, minus 1 third, plus 1 half, plus 6. Let's see, 64 thirds minus 1 third is 63 thirds, which is 21. Actually, I should probably change colors. There we go. So that's gone. Okay. A negative 8 and a positive 6 is a negative 2. Negative 2 and negative 24 is a negative 26 and a positive 1 half. And 21 and 26 is negative 5 plus 1 half, negative 4 and a half. Negative 4 and a half, though, what? Well, we're talking about displacement. We're talking about where it is versus where it was and how much it moved. Since velocity is measured in meters per second, then displacement is going to be measured in meters. So what does it tell me that this thing has a displacement of negative 4.5 meters? Well, I think what it means is from wherever it started to wherever it stopped, wherever it was at time 1 to wherever it was at time 4, it moved left 4.5 meters on that time interval. Right? The stopping point compared to the starting point were 4.5 meters to the left. Okay? Part B says, whoa, wait a second. How far is the total distance that was traveled? Okay, so if this wasn't chapter 7 or 5, to find the distance traveled, we'd have to make one of these charts, right? And we'd have to figure out where t equals 1 is. We have to figure out where t equals 4 is. And we'd have to figure out if we moved right or left or right and how far each of those pieces were. But this is chapter, whatever this is, 5, so we're going to say the distance then is the integral from 1 to 4 of the absolute value of velocity, which I believe is t squared. Yeah, hold on a second. T squared minus t minus 6 dt. Okay? So I'm just going to stop right here and say, I cannot do that. There's no such thing as the integral of an absolute value. I can't do that. So what I'm going to have to do is I'm going to have to figure out where this is positive and where this is negative. And by this, I mean the integrand. And then rip this integral apart and write this as several integrals. So first off, f of t equals t squared minus t minus 6 is a parabola opening up. If I were to graph this thing and make this be the t-axis and this is the y-axis or the f of t-axis, whichever you prefer, then this thing is a parabola opening up. It looks like this thing is factorable, and it should factor into t minus 3 and t plus 2. So it's going to cross the x-axis or the t-axis at negative 2 and over here at positive 3. And so it's doing this number. My job is to find the integral of the absolute value of this thing from 1 to 4. Right? Well, the absolute value of f of t, if I actually graph the absolute value, would look like this. It would take all the negative parts and make them positive, which is going to take this area down here, which is negative, and flip it up to here and make it positive. It's not going to do anything to this because it was already positive. Right? So that's what I need to do manually with the calculus. And so how do I get this piece of the graph down here to flip up and become this piece of the graph up there so I can write that integral? Well, all I have to do to get this piece down here to flip up and become that piece up there is multiply that part of the function by a negative 1. And where do we say this was again here, this intersection? Oh yeah, that's right. We said that happened at x or t equals 3. So I'm going to come over here and say, all right, let's rip this thing apart. Let's rewrite our distance traveled as the integral from 1 to 3 of the absolute value of v of t dt plus the integral from 3 to 4 of the absolute value of v of t dt. Now from the graph and our advanced knowledge of algebra, we know that this piece right here doesn't need the absolute values because the function is already positive. While this piece does need the absolute values because since the function was negative, we need the absolute values to make it positive. So then this problem is going to turn into the integral from from 1 to 3 of negative t squared plus t plus 6 dt plus the integral from 3 to 4 of t squared minus t minus 6 dt. All right, so I just want to stop here and talk about this some more because it does me no good to move on if you're not comfortable with where this came from. This piece stayed the same because we didn't need to change it, because that piece right there is representing that piece of the integral over there that was already positive. This piece we multiplied through by a negative because we had to find a way to make the part that was below the x, or the t-axis, become above the t-axis. So we multiply by a negative 1. And now I'll start doing the calculus. Right? Negative t cubed divided by 3 plus t squared over 2 plus 6t evaluated from 1 to 3 plus t cubed over 3 minus t squared over 2 minus 6t evaluated from 3 to 4. Negative 3 cubed over 3 plus 3 squared over 2 plus 6 times 3 minus negative 1 cubed over 3 plus 1 squared over 2 plus 6 times 1 that's just this first integral plus the second integral 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 3 cubed over 3 minus 3 squared over 2 minus 6 times 3, and that's the second integral. Just left to right, working each piece, figuring out every single silly value. Right? Negative 3 cubed over 3 is going to be a negative 9 plus 9 halves plus 18 plus 1/3 minus 1/2 minus 6 plus 64/3 minus 8 minus 24 minus 9 minus plus 9 halves plus 18. Whew. Let's see. I got a negative 9 and a negative 9 and a positive 18. That's 0. I've got a negative 6 and a negative 24. That's negative 30. Minus 8, that's negative 38. Plus 18, that's negative 20. Right? Let's see, I got a 9 halves, a 1/3, a negative 1/2, a 64/3, and another 9 halves. Well, a 9/2 and a 9/2 is 9. A 1/3 minus 1/2 is a negative 1/6. And a 64/3. Negative 11. All right, I'm going to have to make everything into, what, 6 to make this thing work? So negative 66 sixths minus 1/6 plus 128 sixths. Let's see, 128 minus 66 would be 60, what? 62 minus 1, 61. 61 sixths. 61 sixths, or if you prefer, 10 and 1/6. This is, we're measuring distance traveled. This is going to be meters. Now, one little point to remind you of, since the purpose of this is to find distance traveled, and since we're applying absolute values to make everything negative positive, if you ever get an answer here that is not positive, you're wrong. Check it. Okay? That answer should always be positive. And you know I don't like to speak in absolutes, so the fact that I'm saying always means something. That answer should always be positive. This brings us to the end of section 5.4. At this point, you should be able to do all of the 5.4 homework. The next video will be chapter 5, section 5, our last section for the semester.